Chapter 14, Section 6 is on triple integrals and applications. Our objectives are to use a triple integral to find the volume of a solid region and to find the center of mass and moments of inertia for a solid region. This is a theorem of how to evaluate iterated integrals. Here we have a triple integral Q, where Q represents a solid region of some function of x, y, and z dv. dv is our differential volume. Now, differential volume can be expressed as differential z times differential y times differential x, or dz times dy times dx, where z is bounded between g1 of xy and g2 of xy, and y is bounded between h1 of x and h2 of x, and x is bounded between a and b. So here we have a triple integral. And this Q here represents the bounds that determine a solid region in space. And dV is your differential volume, and your differential volume is dz times dy times dx for this example. Okay, for this example, we want to evaluate a triple iterated integral. We have the integral from 0 to 2, of the integral from 0 to x, of the integral from 0 to x plus y, of e to the x times the quantity y plus 2z, dz, dy, dx. We want to first look at the inside integral. The differential is dz, so you're going to integrate with respect to z. You're going to treat z as a variable, and x and y, we treat those both as constants. Now when you integrate e to the x, we're going to treat that as a constant, so we can leave that constant out in front and then integrate y and plus 2z. The antiderivative of y with respect to z, we treat y as a constant. The antiderivative of a constant is that constant times z. So the antiderivative of y is going to be yz, and the antiderivative of 2z is going to be z squared. Now you're going to replace the z in the integral with the upper bound of x plus y and then the lower bound of 0. When you plug in z equals x plus y into both of these and simplify, what you get is the following double iterated integral. Now we're looking at this. We replace the z with x plus y and simplify, replace the z with 0 and simplify. We get this entire quantity. Now we're going to integrate this with respect to y. Since that is now the inside integral has the differential y, we're going to treat y as a variable and x as a constant. So since we're treating x as a constant, that e to the x is a constant, we can bring that out in front and integrate each of these components with respect to y. The antiderivative of x squared is x squared y. The antiderivative of 3xy, we're treating 3x as a constant, so this could be y squared over 2 times that constant 3x. And the antiderivative 2y squared, we're going to add 1 to the power and divide by that new power to get 2y cubed over 3. Now we just integrated with respect to y, you're going to replace the y with the upper bound of x and with the lower bound of 0 and simplify the result. Okay, when you replace that upper bound with x and simplify, you get this the integral, a single definite integral, 19 over 6 times the integral from 0 to 2 of x cubed e to the x dx. Now this is going to involve some advanced integration techniques, for example, integration by parts, and even perhaps a tabular method of doing that. When you integrate, you will get this quantity here, and then you're going to replace the x with the upper bound of 2, replace the x with the lower bound of 0, subtract and simplify your result. So you get this quantity, 19 times the quantity of e squared over 3 plus 1. So that's an example of a triple iterated integral. You start at the inside looking at the differential from the inside, integrate with respect to that, and then you can simplify that to a double integral. With that double integral, you evaluate the inside integral first, and then you finally get it down to a single definite integral. Okay, for this example, we have a triple iterated integral. The integral from 0 to 9 of the integral from 0 to y over 3 of the integral from 0 to the square root of y squared minus 9x squared of z dz dx dy. Now the order of the differentials does make a difference here, and you want to start with the inside integral. That's your differential z, so you integrate with respect to z and you substitute the z with the upper bound and lower bound. And then the next integral would be the differential x. You integrate with respect to x. Try this one on your own and come back and check your solution. Let's begin evaluating this iterated integral by first looking at the inside integral with the corresponding differential. This has a differential of z, so you're going to integrate with respect to z. So the outside two integrals we will evaluate after we simplify the inside. We're going to integrate with respect to z. The antiderivative of z with respect to z is z squared over 2. And we're going to evaluate that for the upper bound of z equals the square root of y squared minus 9x squared, and z equals 0 is your lower bound. And then when you simplify that, you will get a double iterated integral. Now, I do want to point out that I do write the z equals 0 and z equals the upper bound. I write that out so I remember which variable to plug in. Okay, when you plug in the upper bound of z equals the square root of y squared minus x squared and you square it, that quantity becomes so y squared minus 9x squared all over 2. And I can write that as a 1/2 out in front, or treat it as a constant. I could even bring it all the way out if I wanted to. Or I can divide each of those by 1/2, or divide each of those by 2. I'm going to leave it like this. And then when you plug in 0, you get 0. So here is your double iterated integral. Now we're going to look at the next inside integral. Here we'll look at this inside integral. The differential is dx, so we want to integrate this with respect to x. Again, that outside integral, we're going to wait until we simplify this inside integral before we evaluate. We're integrating with respect to x, so we're going to treat x as a variable and y as a constant. That antiderivative, I'm going to also include that 1/2. The antiderivative of y squared with respect to x, we treat y squared as a constant, so that's going to be y squared x. And then the antiderivative of 9x squared with respect to x is going to be that x to the third power, divide the 9 by 3. And then we are going to evaluate that for x equals 0 to x equals y over 3. Now when we plug in the upper bound for x, we get of y over 3. We can begin to simplify this. We get the integral from 0 to 9. That 1/2 is a constant. Now we're going to plug in y over 3. So y squared times y over 3. That's going to be y to the third over 3. And then we're going to replace the x here with y over 3. Now we're going to raise it to the third power. So it's going to be minus 3 times that quantity of y over 3 to the third power. And then when we plug in 0 for x, we get 0 for everything. And you end up with this single definite integral. Let's simplify it a little bit. So we get the integral from 0 to 9. This 1/2. Okay, this y to the third over 3, right, is y to the third over 3. Y to the third over 3 to the third, along with this 3. This would be a 3 in the numerator and a 3 to the third in the denominator. So that's going to be 3 to the second power in the denominator. So that's going to be minus 1 over 9 y to the third. then we have our dy. And this simplifies to the integral from 0 to 9. Here we have a third minus a ninth, and that's going to be uh, 2/3 with the one half, or 2/9, sorry, with the 1/2 out in front, and that we will get 1 over 9 y to the third dy, and you can integrate that and you would get approximately 182.25. So that's our example of evaluating a triple iterated integral. Begin with the inside, evaluate that. We integrated that with respect to z, and then we got it to a double integral, and we evaluated the inside integral with respect to x, and then you got it to a single definite integral.